Alright, welcome to video 8.1 where we transition from the 2D world to the three-dimensional world for the first time. And so up to this point in chapter 7 we talked a lot about bonding and the octet rule and how things bond, and where electrons are in atoms and in molecules, and we have multiple accounting mechanisms for that now. But ultimately, what we'd been doing in all of these cases was rendering a two-dimensional representation of an intrinsically three-dimensional world, right? All of the molecules that actually exist are three-dimensional in nature, and that third dimension is really important when we think about bonding. So how do orbitals arrange themselves around an atom, and how can those orbitals come together to overlap to share electrons to form the bond? In which case, to answer that question, we really need to translate what we have now as two-dimensional into three-dimensionals, and that gets us into this concept of molecular shape. So I've got the three Lewis structures for three common molecules written up here. I've got water on the left, ammonia in the middle, and methane in the center. And these are the two-dimensional representations that we've, in the last chapter or so, gotten pretty accustomed to. But they don't tell us anything about the three-dimensional structure of this thing, so we need to translate to the next dimension. The actual three-dimensional structures for the molecules are in the center here in the colored version. So water actually takes on this sort of bent-like structure. Ammonia's got this almost pyramid-shaped structure, and then methane has the same sort of pyramid structure, except that it's got its fourth bond just sticking straight up. And what you can see below that is a representation that's really similar to the Lewis structures that we've shown before, but there's some different representation here. Let me walk you through that. So think about this as a two-dimensional molecule, water. It's three bonds, and if you're looking at the screen now, watching this, these straight lines that are depicted in this representation, those are in the plane of the screen. So this hydrogen, this oxygen, and this hydrogen, if you imagine these all on a sheet of paper in front of you or on the screen, they're bisecting that piece of paper. They're all in the exact same plane with each other. That's what that straight solid line indicates. So if we go over to ammonia, we can see that we've got a couple other representations here. We have, again, that straight solid line right here. So that means this nitrogen atom and this hydrogen atom are in the same plane. But we then have this bold wedge shape here. This bold wedge means that that bond is coming out of the plane, meaning it's coming towards you as you're looking at it. And then the dashed line here means it's going into the plane. And so this is one attempt to, on paper, represent two-dimensional molecules, and it feels cumbersome, but it turns out this will become second nature to you in no time. And this is how all molecules are represented going forward in chemistry, especially when you get to organic chemistry and biochemistry. So if we look at methane, the same is true here. We've got this hydrogen and carbon bond and this hydrogen carbon bond. These three are all in the same plane. So imagine these are all stuck together in one sheet of paper. They're all existing in that plane, and then this hydrogen is coming out at you, pointing right at your face, and then this hydrogen is pointing exactly opposite of you. So we're able to start to represent this sort of three-dimensional structure with this notation. So how do we know how molecules are going to arrange themselves in three-dimensional space? There's lots of models out there. The first one we're going to learn about in this class is this thing called Vsepr. It's an acronym. People sometimes call this Vsepr or Vsepr, depending on who you learn it from. I tend to call it Vsepr. That's how I learned it, but it's interchangeable. It stands for valence shell electron pair repulsion. And it's a model. It's not anything absolute. It's just a model that chemists came up with that helps describe three-dimensional structures of molecules. generally how this works is exactly what the name implies. Electron pairs, because they're negative, because electrons are negative, when they get in close proximity to each other, they begin to repel each other in space. And so we can think about bonds like in water, where there are electrons in each of these bonds. These things are going to point far away from each other simply because they repel each other in the bond. And so this valence shell electron pair repulsion theory is really based on thinking about where the electrons are around an atom and getting them as far away from any other electrons on adjacent atoms. And whatever that sort of lowest energy or lowest repulsion structure that you can form, where electrons as far away from each other as they possibly can be, that's typically the actual three-dimensional geometry that you would measure for that molecule. So it's a pretty nice, powerful tool. All right, so in applying this Vsepr model to evaluate what a two-dimensional structure might look like in 3 dimensions, we start with the first step, which is drawing the Lewis structure, so drawing it in 2D. And then we count the charge clouds that are around it. And we haven't talked about charge clouds yet. So charge clouds are anything around a particular atom that is a lone pair or a bond that occupies some space around that. That could be a radical, meaning a single electron. It could be a lone pair. It could be a single bond, a double bond, a triple bond, etc. So as an example, if we just had, this is a made up, this isn't real, but so we'll just say some central atom X, and we have it bound like this to 4 different things, we would count this as 4 individual charge clouds. And the reason we're thinking about charge clouds and not specific electrons is these groups of electrons are going to move together because they are in one bond, one orbital. They're not going to move independently of each other. So one way to think about this, and typically in class I do this with balloons, you can think about this is a central atom X, and each of these bonds is a balloon that's tied together. What happens when you tie 4 balloons together? Well, they repel each other based on their size, and they form their own independent clouds, and they form their own low energy structure. It's exactly analogous. You could think of each one of these charge clouds as a balloon in real space, and however this would organize itself if you had 4 balloons tied together, that's exactly how it would organize itself at the molecular level. Let's think about this with another example. So if we have some other sort of generic atom, and let's say it's got a double bond to something out here, and it's got a single bond to something out here, and it's got a lone pair here. A charge cloud is each one of these chunks of electrons or of electron density that cannot move independently of the other of itself. So in this case, the double bond, those 2 bonds can't move independently of each other, so we count that as 1 charge cloud here. The lone pair moves together because that's stuck in 1 orbital, so we count that as a charge cloud. And then the single bond, of course, we count as a charge cloud. So we'd say this generic atom has 3 clouds surrounding it, or in other words, it has 3 balloons surrounding it. And they're going to organize in space based on the repulsion of those balloons or those 3 charge clouds. All right, the second step then is once you have the Lewis structure drawn and the charge clouds identified around each atom, you then want to predict the 3-dimensional geometry as if those clouds could orient as far apart as possible. So again, thinking about them like balloons. So each charge cloud is a balloon. What is the orientation of the geometry that the structure would take if they were as far apart, as if each of those clouds was as far apart as possible? So the simplest orientation is if you just had 2 charge clouds on an atom. In that case, let's do an example. You might have something like carbon bound to oxygen, double bonded here, and double bonded here. This is CO2 molecule. So if we look at the central atom here, we can identify first how many charge clouds it has. So it has 1 here, and it has one here. So there's two clouds on this molecule. Imagine these like two balloons. What's the furthest two balloons could get apart from each other if they were tied in the center? Well, they would just be in opposite directions. And so in this case, for two charge clouds, the bond angle is going to be 180 degrees, and we're going to call this molecular geometry linear because it forms a straight line. We don't care about the structure around these peripheral atoms because it's not bound to anything else, right? The peripheral atoms don't dictate the overall structure of this molecule. It's only the central atom in this case because it has two objects bound to it. Another example would be HCN. So HCN, the Lewis structure looks something like this. Charge clouds on carbon, we count this single bond as one, but we also count this triple bond as one because these can't move independently of each other. So two clouds, they're going to point as far away from each other as possible, and so that's going to be a bond angle. And by bond angle, I mean the angle through here. So this angle is 180 degrees, which means it's going to be a linear structure. So two charge clouds, that's as simple as it gets. We have a nice linear molecular geometry. So with three charge clouds, we actually have two different subcategories of molecular geometry that you could obtain depending on the specific structure. So the simplest one here would be the formaldehyde molecule. So the Lewis structure looks something like this. We'd drawn this in a previous video. So we've got that as the Lewis structure. We have three charge clouds around the carbon, right? We have one here for the single bond, one here for the single bond, and one here for the single bond. So those are three balloons. What's the furthest three balloons could get away from each other? Well, they would form, they would stay in the same plane with each other, and they would sort of form this triangle shape, right? So you'd end up having something that looks like this, all in the same plane with carbon in the center. That's as far away as they could get, and the bond angle between these would be 120 degrees. We would call this arrangement, this molecular geometry, trigonal planar. In this case, in a perfect system, if you had single bonds in all three of these atoms, then you would have a perfect trigonal planar arrangement where all three of the angles would be exactly 120 degrees. In this case, look at this molecule and try to identify where you think there'd be more or less electron density in different bonds. Hopefully you are looking at this double bond and you're saying, well, there's 4 electrons there, but there's only 2 electrons in each of these. And so if we're thinking about this as a repulsive force, then there's going to be a little bit more push from these 4 electrons on those balloons than there will be in that other direction. In that case, the actual bond angle of this structure, because there's a double bond at the top, we'd still call this trigonal planar, but the bond angles wouldn't be a perfect 120. In this case, this bond angle would probably be about 117 degrees, whereas this bond angle here would be about 122 degrees. So you would be squeezing the two legs of this pedestal closer together and opening up this bond angle here, simply because you've got 4 electrons here. So that's useful to know. I could ask you a question like that. If you had 3 single bonds, though, we'd still expect 120 degrees each. Okay, so the second flavor of 3 charge clouds is slightly different. So the first one I mentioned was trigonal planar, and that's when you have these 3 bonds that are formed, and they fall within this nice perfect triangle. The angles might be 120, they might be slightly distorted depending on whether you have a double or triple bond there. Another example would be this molecule SO2. And so SO2, if we look at the central atom here, it's got this one single bond here that forms a charge cloud. It's got a lone pair, and then it's got a double bond. So it's got 3 charge clouds, which is why it fits into this category, even though it's only got 2 bonds. And so it can be a little misleading. So 3 charge clouds, but only 2 bonds. And so that gives it a unique structure because even though this is causing distortion, it's not actually a third bond, so it's not going to form the same sort of trigonal planar structure. You can still think about these as sort of the same balloons pushing against each other in space. And so what you end up with, the actual molecular geometry, if you were to think about this without any of the other stuff here, you would have S, O, and O. That's not a trigonal planar because there's nothing up here, right? There's nothing up top. So all we have is a structure that looks like this, in which case we call this a bent structure. Something very similar that falls within this category would be water. So water, actually, I'm sorry. We'll get to water here in a second. So SO2 has this bent structure. It's got 2 bonds, 3 clouds, bent. Trigonal planar's got 3 bonds, 3 clouds, which gives rise to that trigonal planar shape. Okay, so moving on to 4 possible charged clouds around that central atom. I've got 3 different flavors here. So I'll go through each of these, A, B, and C. So we're starting with methane. This is the simplest one. So methane, if we draw its Lewis structure, would have something that looks like this, right? But that doesn't, if we interpreted this literally, it would look like we had all of these atoms all in one plane or all on one sheet of paper, but that's not the three-dimensional realistic picture. Instead, if you have 4 charge clouds, what are the 4 ways, or what is the geometry that 4 objects could take to get as far away from each other as possible? If they stayed within the plane like this, then the bond angle here would be 90 degrees. That'd be as far away as you could get while still staying in the plane. But that actually isn't the furthest away that 4 objects could get in space if they're all tethered to the same central atom. In that case, they can look like this, and I'm going to use the sort of formalism that we used before, where I have a straight line to indicate a bond that forms in the plane. So I've got a carbon-hydrogen bond in this plane, I've got a carbon-hydrogen bond in this plane, and then I've got a carbon-hydrogen bond, and I use this wedge that's coming out at you, and then I've got this dashed line, which means that carbon-hydrogen is poking back into the plane. We call this shape a tetrahedron or a tetrahedral type geometry. And so the simplest 4 charge cloud geometry is 4 objects in space all pointed as far away from each other as they can, which forms this nice tetrahedron. And in that case, the bond angle is 109.5, which is greater than 90, which is why a simple planar molecule is not as good as the full tetrahedral. You buy yourself almost 20 degrees further away from each other in that case. Okay, let me pause and I'm going to show you what that looks like in 3 dimensions. It's better than my drawing. Okay, so I grabbed this from your textbook to help visualize what this structure looks like. It takes a little practice to look at this molecule and recognize it as a tetrahedron. So think about the center here of this tetrahedron. That's where the carbon atom is, and that each point of the tetrahedron, that is your hydrogen atom. Those bond angles there are 195 or 109.5 degrees. This structure that I have drawn here is exactly the same as representing it as this regular tetrahedron down here, or as the structure like this, or as the structure like this. The purple structure that I have handwritten, that's the formalism that chemists use when we're writing by hand, because we're not going to spend the time to draw out a 3-dimensional structure like this, nor are we necessarily adept enough to do that. And so take some practice to look at a structure like this and immediately see it as something like this, but that's what you're doing in this class. So we'll practice a lot. So the Lewis structure for NH3 is going to look like this. Doesn't tell us anything about the geometry, but it does tell us that we've got this lone pair, which is going to be a charge cloud. That's a charge cloud. That's a charge cloud. And that's a charge cloud, so that's why it fits into the category of 4 charge clouds. But in this case, it's different than methane because we've only got 3 bonds. So 3 bonds but 4 charge clouds, whereas methane had 4 bonds and 4 charge clouds, similar to what we just talked about with the 3 charge cloud issue. So 3 bonds and 3 charge clouds is going to give rise to a molecular shape that looks like this. You've got the nitrogen here. This lone pair here is actually going to exert quite a bit of distortion downward on this structure. And so even though there's not a bond here, it's still going to act with repulsive force. And so you're going to end up with, I like to draw this explicitly, you don't have to. I like to draw this as an orbital with the lone pairs there just to remind you how they exist. And then I'm going to have hydrogen in the plane. I'm going to have a hydrogen coming out of the plane, and I'm going to have a hydrogen going into the plane. And so that's going to give you sort of this pyramidal structure that I'd shown you before, where you can think about these all forming the base of a triangle, all pointing upward towards this central nitrogen. There's no actual atom up here, so we don't visualize that. All we see it as is a sort of pyramid without anything at the top. I'll paste in here an example of what that would look like. Alright, so we've got the sort of computer-generated graphic here. And maybe a little bit easier to see, where you've got the 3 hydrogens all pointing downward here. The blue atom is the nitrogen in this case. There's nothing up here, just the repulsion from the lone pair of electrons. You can see that the bond angle here is not exactly 109.5, it's actually 107 because of the distortion, the pushing from the lone pair electrons at the top. So the last subcategory of the 4 charge clouds is going to be water here as an example. And actually I forgot to mention, so this structure, the name of a molecule that has 3 bonds and 4 charge clouds is going to be trigonal pyramidal. Trigonal meaning 3 and pyramidal meaning the shape is like a pyramid. Okay, so back to water over here. So water, this is the Lewis structure. We've got 1 charge cloud, 2 charge clouds, 3 charge clouds on that lone pair, 4 charge clouds on that lone pair. Of course it has 4 charge clouds, but it's only got 2 bonds. So you can sort of see the theme here. Within the number of charge clouds, then we have subcategories dependent on how many bonds that molecule can form with those distinctive 4 charge clouds. So this molecule, the way it's going to actually take a 3-dimensional shape, it's going to look more like this. So these hydrogens are going to get pushed downward, very much like the tetrahedral or the trigonal pyramidal case, but in this case you've got 2 lone pairs hanging out up top here, and those 2 lone pairs are going to exert a reasonable amount of repulsive force to bend those legs back down from being simply a linear molecule. So even though it's only got 2 bonds, just like our CO2 example, it's got these extra lone pairs on the central atom that further distort or wrench on this thing. And the bond angle between here is roughly 104.5 degrees because of that, and we call the molecular shape of this thing bent. Pretty creative. Alright, let me show you a picture of that. Alright, I got all 3 of them pasted in here just so that we can look at them side by side. So these are all the 3 different flavors of 4 charge clouds. So we've got the 4 bonds in this top example that formed the tetrahedral shape. We've got 3 bonds, that was our ammonia example, that gave us the trigonal pyramidal shape. And then we've got the 2 bond option like water, and that gives us this sort of bent shape. This bent shape has huge implications for the physical and chemical properties of water, and really not to be you know, to overstate this, but the reason why the Earth exists at all and why life exists on Earth is really because of the bent shape of the water molecule. If it weren't bent, if it were linear instead, then we wouldn't be here. And we'll talk a little bit about properties in a couple chapters as to why that's the case. All right, moving on to 5 charge clouds. 5 charge clouds gives us 4 subcategories of molecular shape. So I'm not going to spend a bunch of time drawing these because otherwise this video will be 2 hours long. But I'll borrow some versions here. So we'll go through A, B, C, and D here. So the first example would be this PCl5 molecule. So in this case, you've got 5 clouds and 5 bonds. So again, that's the simplest case we start with. So you've got 5 of these chlorines. You can tell by the way that this is drawn that the 3 bonds here that I've highlighted in red, those are all in the same plane. And then you've got a chlorine poking out at you and a chlorine poking back at you. And so that this structure to the right is what this would look like three-dimensionally. Both of these are equivalent, right? So you should get accustomed to seeing the same picture in both of these cases and drawing it yourself. And we call this molecular shape trigonal bipyramidal instead of trigonal pyramidal. And the idea here is that if you look at this sort of triangular shape that gets formed in the center, we then have a pyramid that forms this direction and a pyramid that forms in this vertical direction, and that's why it gets this bipyramidal shape. Okay, so let's look at B here. Again, 5 charge clouds, that's why it's in this category, but it's only going to form 4 bonds to this sulfur, which means it's got this big old lone pair hanging out here that's going to distort this shape slightly. And so what we get is a shape that looks like this. These 2 shapes are equivalent. This is just rotated 90 degrees this way to give you another image of this. We call this orientation of the SF4 molecule the seesaw shape. The seesaw being this picture here, where you could have, let's see if I can draw it, a human like this on here and a human like this on here, and you could rock back and forth on this seesaw. That's where it gets its name. So 4 bonds, 5 charge clouds gives you the seesaw shape. Jumping over here, now we're at 5 charge clouds but only 3 bonds based on the octet rule of this molecule. This is ClF3. So again, now we've got Cl in the central atom, and you've got 2 of these original, so you could think about it like this original trigonal bipyramidal molecule, but imagine we got rid of that and got rid of that and just replaced them with electrons, right? That's what you have over here now. So there's no bond here and no bond there. So what you have is just a T shape based on the distortion of where those electron clouds are. And then the final option here doesn't come around. There aren't that many examples of this, but they do exist, where you still have 5 charge clouds. So 1, 2, 3, 4, 5, but you've only got the option of forming 2 bonds. In that case, all 3, if we go back to our original trigonal pyramidal structure, all 3 of these, the sort of triangular plane, all 3 of those are gone. And so all you've got is this straight line of molecules. And so this actually takes on another linear shape, similar to the linear shape we saw with 2 charge clouds, except this has 5 charge clouds, and it drives the formation of this linear chain. So this is the triiodide molecule. Okay, 6 charge clouds here. We've got 3 options. So we're at the end of the rope here. We don't have any more of these to talk about. So we've got our A option, which actually encompasses both of these. These are just 2 representations of the same thing. We've got B down here, and we got C here. So 6 charge clouds. If we have 6 charge clouds and 6 bonds, that's the simplest example always, then we have this top scenario. Imagine if you have a central atom here, like this, and then you've got 6 red objects all positioned equidistantly around it. the furthest those things could get away from each other is to form this shape called a regular octahedron. Regular octahedrons are symmetric along each axis, which means that it doesn't matter which way you look at this thing, it's going to be symmetric. So this is showing the side view, this is showing the top view. So this thing's symmetric in every direction, where you have 90-degree bond angles at each point. So the actual example, this is just generically showing you what octahedron is. A real molecular example is the sulfur hexafluoride, or SF6 molecule. And this thing is just perfect octahedron. So really high symmetry, interesting molecule. So still under the 6 charge category, but if we have 5 bond capability, then you can get something that looks like this. This is antimony pentachloride ion. This is actually a superacid. This is a really interesting molecule too. So imagine the original octahedron up here, but you just nix one of these. It doesn't matter which one because it's symmetric. You nix one of them, of those atoms, and you replace it with a lone pair. That's going to give you this nice sort of flat bottom, this flat rectangular bottom with a pyramid shape at the top. So we call that a square pyramid shape, or square pyramidal, instead of a trigonal parameter, because the base of the pyramid is square shaped. So pretty straightforward. And then our last possible molecular geometry, this is a really interesting one, is when you have 4 bonds in a 6 charge cloud scenario. So 1, 2, 3, 4, 5, 6, so all 6 of them. Now the lowest energy conformation for this object is going to have the 1 lone pair pointing up, 1 lone pair pointing down, and then all 4 of the peripheral atoms remaining in one plane with 90-degree bond angles through each. That's going to be the furthest away these charge clouds can get from each other, and so we get this perfectly square flat molecule, which is really fascinating, and we call this a square planar shape. There's some really some actually pretty interesting anti-cancer drugs. Some of the earliest chemotherapies were based on this thing called cisplatin, which was essentially platinum chloride in this shape, in this square planar shape. So it's got a really interesting molecular geometry. So just a quick summary. You probably can't actually read all of this, but that's okay. This is in your textbook too. This is just showing everything we just reviewed. So looking at the different geometries based on the different numbers of charge clouds, the different numbers of bonds, and the different numbers of lone pairs. So we could sort of subdivide this table and say everything up here, that's 2 charge clouds. Here's 3 charge clouds with 3 and 2 bonds. Here's 4 charge clouds with 4, 3, and 2 different bonds. Here's 5 charge clouds with 5, 4, 3, and 2 different bonds. And then this last one is what we just covered, which is 6 different charge clouds with 6, 5, and 4 different bonds. So you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 different geometries that molecules can take based on 1, how many charge clouds there are, and then 2, once you know the charge clouds, how many bonds form. So practice, practice, practice. This will make it a little bit easier to think about these. I will give you a sheet that gives you a list of the actual shapes for these. So I don't really want you to memorize these. They're helpful to know if you continue on in chemistry, but I don't want you to memorize them overnight. That doesn't serve you well. So I'll give you a sheet that's similar to this. What I want you to be able to do are the types of examples I'm going to walk you through after this, where I give you a molecule, maybe BRF5, which we're going to do in a second, and I want you to, 1, draw the Lewis structure of this, 2, count how many charge clouds it has, and then 3, be able to evaluate what its molecular geometry would be based on a table like this, and then 4, I'm going to ask you whether or not the molecule is polar. So that's going to go back to this idea of partial positive, partial negative, and polar bonds.